Good afternoon and welcome to today's webinar on smoke detection in challenging environments. My name is Morgan Hurley and I'm the Technical Director of the Society of Fire Protection Engineers. This webinar is sponsored by Xtralis. I would like to remind all of you that if at any time you experience audio difficulties or problems advancing the slides, simply press your F5 key to refresh your webinar console. I would also like to encourage all of you to ask our panel questions. As a question occurs to you, simply type it into the box on the right-hand side of your screen, and we will address as many of your questions as we can at the end of our presentation. FPE will award 0.1 continuing education units to everyone who attends the entire webinar. You should receive your CEU certificate by email within a week or two from today. Let me now introduce today's presenters. Claudio Grappetti has more than 30 years' experience in the design, development, and marketing of special hazard gas and fire detection equipment, including optical flame detectors, chemical and optical gas detectors, smoke detectors, aspirated smoke detectors, and multi-hole aspirated gas detection. He currently serves as the Global Vice President of Business Development for Gas Detection and Environmental Monitoring for Xtralis. Steve McGee has 22 years' experience in the fire and life safety industry. For the past 2.5 years, he has worked for Xtralis, and he is currently the Business Development Manager in the Americas for OSID and the Regional Sales Manager for Texas and Oklahoma. Previous to Xtralis, he was a District Manager for a major fire alarm equipment manufacturer, and he has over 15 years' experience in the sales, design, and installation of fire alarm systems, including air sampling smoke detection. He has an economics degree from the University of Texas at Austin and is NICET certified. Claudio, the floor is yours.
Thank you very much, Morgan, and welcome everybody. Thank you for taking time out of your busy schedules to join us today. As you can see, the topic of our discussion today is smoke detection for challenging environments. Taking a look at what we're going to cover today, it's going to be a range of topics, beginning with trade-offs we face when designing systems. We'll then review what challenging environments are, followed by a quick overview of available technologies. Open area imaging detection will then be discussed, followed by a discussion of very early warning smoke detection. We'll review detector design methodologies and their impact on detector performance. And we'll also review a new Industrial ASD device recently introduced to the marketplace with a few examples of successful deployments. Then I'll close the session by presenting a aspirated smoke detection requirements matrix. We're all familiar with the basic fire triangle. What I'd like to introduce to the group is the concept of a detection triangle, where the three sides consist of the ability to detect a fire, the tendency for nuisance or false alarms, and the cost of installed systems. The objective of the detection triangle is to highlight the interdependence between detection capabilities, the occurrence of false and nuisance alarms, and the total cost of ownership of a system. When this balance is achieved, the net result is an optimum detection solution. Selecting a detection technology that provides the highest level of detection to ensure protection of property, life, business continuity, and the environment is essential, while at the same time delivering a solution at an affordable cost, both from an initial installation and long-term operating perspective. Now we're going to discuss the various attributes associated with challenging environments. There are some obvious environmental conditions that make detection difficult, causing false alarms or nuisance alarms, or shortening a detector's life. Additionally, large open spaces with high ceilings or high and variable airflows complicate detection. There's a long list of environmental factors such as dust, dirt, temperature extremes, water, or even the presence of toxic gases, to name a few, that can degrade the sensitivity and shorten the life of a detector. Selecting and designing a detection system is very important, but perhaps one of the most overlooked and underestimated factors that contribute to a high-quality, high-reliable safety system is a system's installation and maintenance. Inadequate installation or maintenance can destroy the integrity of a system. High ceilings, confined spaces, elevator shafts, equipment racks, all of these present accessibility issues that can interfere or compromise routine maintenance. Restricted access areas, although not necessarily harsh or challenging environments, can make access difficult, and this also can interfere or prevent routine maintenance from being performed. When prevention of vandalism or tampering is important for your facility, the ability to install a detector in an unobtrusive manner is required. Same can be said if you have some historic buildings or building aesthetics that need to be preserved. When evacuation involves large numbers or people that require assistance, the earliest possible reliable detection and notification is critical. This is a simple overview of detector performance characteristics that I've put together to show the relative differences between the various detection technologies that are available. The relative ranking could and will change depending on the specific application. In this case, I've selected a large open space with high-value content. It shows that aspirated smoke detection affords the best sensitivity to smoke, followed by laser detectors and open-area imaging detectors. It also highlights that ASD would be the best suited to prevent damage to both structural members of the building and or building contents. Aspirated smoke detection, open-area smoke imaging detection, and linear heat detection is shown to be the most tolerant to a wide range of environmental factors. Additionally, this example highlights the fact that as the size of the space increases, the initial cost differential between spot detectors and aspirated smoke detectors is lessened, if not reversed. It also shows that for large areas, the cost of equipment and installation for both ASD and linear heat are in fact similar. Steve McGee is now going to take a few minutes and present open area imaging. Steve, it's all yours.
Okay, thanks, Claudio. In this section of the presentation, we're going to provide an overview of open area smoke imaging detection. Specifically, we'll explore what dual wavelength open area smoke imaging detection is and some of the challenges that it can solve. Historically, beam detection has proven to be a challenging proposition. This is a sample list of the many things that have caused problems with single light source beam detectors. Innovations have yielded some success in overcoming these challenges, but false alarms because of these things are still commonplace. What makes dual wavelength different? There are four major improvements to the technology when compared to traditional single IR beam detectors. First, two wavelengths of light are used, both UV and IR. Secondly, a CMOS imaging chip with many pixels, the same technology you would find in your digital camera, is used instead of a single photodiode beam. This provides a wide viewing angle to locate and track emitters. As a result, the system doesn't require precision alignment and can compensate for drift caused by natural shifts in building structures. The time for installation has been measured to be at least 50%, sometimes up to 60 to 70% faster. In fact, the wide viewing angle enables multiple emitters to be used with a single imager. The imaging chip also provides automatic alignment and movement tracking by software in the imager. Third major distinction is its unique method for alignment. A ball and socket housing allows a wide range of horizontal and vertical movement. A simple laser screwdriver tool is used for alignment. And fourth, smarter algorithms have been introduced. The three primary challenges that cause problems with traditional beams are large particle rejection, building shift causing misalignment, and foreign light intrusion. We'll address each of these challenges. This slide shows 3 different scenarios, and I'll explain how a dual wavelength beam transmitting to an imager reacts to each. Both UV and IR wavelengths outside the human visible range assist in the identification of real smoke compared to larger objects such as ladders, insects, and dust. The 2 wavelengths allow the imager to not only distinguish the size of the particles along the path, but also distinguish the difference between smoke and dust, for example. The shorter UV wavelength interacts strongly with both small smoke-sized particles and large particles, while the larger IR wavelength is affected only by larger particles. By comparing the relative strengths of the 2, the detector is able to provide repeatable and reliable smoke obscuration measurements while rejecting dust and other solid objects. The use of 2 beams provides the system with a far superior decision-making process for triggering alarms on smoke while minimizing nuisance alarms. In the bottom scenario, a blockage is shown. The imager loses signal from both beams and will report a trouble, not an alarm condition. If the imager is set on non-latching, once the blockage clears, it will reset itself. Momentary obstructions such as, say, a bird, balls, forklift passing through will not result in an alarm or trouble signal. The middle scenario shows dust along the path of the beam. Dust particles are large, so the imager will see a small loss of both UV and IR. In this case, it will reject the dust and no alarm or fault condition is reported. In the very top scenario, smoke crosses the path of the beam. Smoke particles, being smaller, interact much more strongly with UV than IR, which causes the imager to recognize that it is a smoke condition and it will trigger an alarm signal. There are powerful benefits afforded by the use of open area smoke imaging, specifically the dual beam smoke imaging. The picture shown here is the actual field of view of a 45-degree imager. The diagnostic software is used to produce this image. It's not required to set up the devices. However, it can be useful to make sure that the emitter is actually located in the field of view of the imager. In this case, you'll see 4 emitters in the field of view. The imager locates and tracks the position of each of these emitters anywhere within its field of view at a pixel level, which allows it to operate under conditions where structure, vibration, or movement exist. In this case, it would take a tremendous amount of movement for the emitters to move out of the field of view of the imager. In fact, the wide field of view allows a plus or minus 2 degree of building movement. At only a distance of 330 feet, this would equate to plus or minus 12 feet. Almost unheard of in the beam detection industry. Installation and commissioning is really a breeze using dual beam smoke imaging. It's simple. The exact alignment is not required. A unique laser alignment tool is used to only roughly align the emitter at the imager. You'll see one in the picture. This can result in up to a 70% savings in the setup time required, not to mention going back to reset beams that have been misaligned due to various factors. In addition, when lifted to the maximum of 20,000 square feet, it can outperform traditional beams by up to 50% in length, presently almost 500 feet in length of coverage for one beam detector. Building movement is the #1 cause of false alarms with beam detectors. Correct alignment and commissioning takes the best part of the installation, and it has to be exact, varying from 1 to several hours. Sometimes it even takes 2 technicians to do the work. So instead of gun sights, sight holes, mirrors, thumb wheels, LED and beep aids, and including intensive training on how to set one up, dual beams can be aligned with a simple laser scenario. Because of the only roughly alignment, it can be done in just a matter of minutes. What we'd like to do next is take a look at some real-world problems solved by dual wavelength smoke imaging detection. I'd like to mention it works just fine in normal environments. We're showing the more challenging ones today. Anywhere that a traditional beam would be installed, we could use a smoke imaging device. Let's take a look at long distances. Traditional beams using a single IR wavelength pick up all the airborne particles, which may include anything from dust, steam, dirt, water droplets, etc., you name it. This could result in an amount of obscuration that can be quite elevated during the day. Because of this, traditional beams have to limit their length to sensitivity and vice versa. In fact, it would be hard to have a traditional beam even at a 20% setting at 325 feet. Open area smoke imaging is unique. It can reliably operate up to 500 feet, again possible only because of both UV and IR being used as the signaling. As both wavelengths are equally affected by larger particles, the possibility of false alarm or trouble signals is almost eliminated. The next slide is an industrial site that's used to construct modular hospital compartments. There was a beta test set up, and a 90-degree imager and 2 emitters were deployed. One beam was installed over a challenging paint section, so they were concerned with vapors, and the other over a less dirty control area. The field of view for the imager was only 6 inches. Because it has a wide field of view, it could be set up in that tiny space. The better types of motorized beams need to actually see aside the reflectors they use in order to learn the overall position of the reflector, hence requiring anywhere from 18 to 24 inches of space even to operate within. The detectors at this site were exposed to vibration. There was a large crane that hauls large concrete panels in and out of the building, so the building would shake. It was installed, worked perfectly over 3 months without any faults or false alarms. The value here to the customer is they had already resigned themselves that the only option was to use a linear heat type device instead of smoke detection. Now they could use smoke detection in the particular space. This site presented a combination of various challenges. We had long-range detection, a low landing ceiling, and limited space between the roof of incoming metros and the ceiling. The dual wavelength beams were crossed over the tracks to avoid interruptions that might have occurred if deployed over the landing areas. This meant that the beams had to be able to operate in a narrow space each time the metro came into the station. The beta testing went fine. It's since been installed and is operated now without issue for over a year. This slide's very interesting. A beta installation was set up and extensive smoke testing was done at the York Minster Cathedral at the request of the health and safety manager at the Minster. A fire at the cathedral in July 1984 is still vivid in their minds today. The beta test proved that open area smoke imaging could reliably detect smoke at 72 feet high. The test also indicated what sensitivity setting would be optimal based on the various test fires. An interesting background increase was logged and brings us to the next slide. You'll see a spike in the graph, and it's shown in more detail there. It was identified to have happened at the end of the Minster's Pentecost service when 6 Viking-style torches were lit and carried down the nave. The graph shows that the dual wavelength beams could have picked this up if sensitivity was set at the 20% level. The UV signal reached 33% obscuration, while IR is just touching the 20% mark. This demonstrates the better and higher sensitivity of a dual frequency detector. Obviously, 20% wouldn't be the setting in this particular case. This sort of information, though, is invaluable when trying to determine the best method of protecting priceless historical sites and at what sensitivity level the smoke detection should be set at. Here we have a semi-open warehouse. A beta trial was organized over the winter for the purpose of evaluating the effects of cold and condensation. The existing beam detector that were installed had many false alarms in the past. Various arrangements were tried. None of them seemed to work. Open area smoke imaging was installed, performed without fault or alarms during the whole winter period. You'll see on the graph the spikes are caused by the condensation. Another quite interesting scenario, you find a lot of them in certain parts of the country here in the U.S., chicken farms, particularly those with free-running chickens. They'd like to have smoke detection. They resign themselves to linear heat detection. And what happens is if you put in a traditional beam, when anybody walks in the building, the chickens are stirred up, a lot of dust and feathers are generated, and alarms are caused. A test installation showed that open area smoke imaging could reliably detect smoke in this environment without problems or false alarms, provided that care is regularly taken of cleaning the lenses. They realized after 90 days they needed to wipe the lenses off. It's a great example of where smoke detection could be utilized in lieu of only heat detection. The next site is a facility that prints packaging boxes. And what happens is the owner sprays a water mist every few minutes to maintain a humid environment. This happens 24/7, would cause a lot of problems with any spot detectors, and specifically traditional beam detectors. Open area smoke imaging was tested for a few days. No water droplets or condensation occurred on the imagers or lenses. One can notice the high obscuration, around 50% in the graph there, that each time the mist is re-released. This is a textbook example of where this technology works. Dual wavelengths utilizing UV and IR values did not cause false alarms, and again, they could have smoke detection in an environment they thought not possible. Let's take a look at a recycling plant. Traditional beams were ordered for this site. Unfortunately, due to the extreme amount of dust generated in the air all day long, the installer couldn't even set up the original purchased product. Open area imaging was tried in the worst part of the site. The results after startup without any problem showed dust averaging 25 to 30% obscuration. As there was no difference between UV and IR, no false alarms occurred. Extrapolating the log data indicates that at least monthly cleaning of the lenses would be required. Obviously, this wasn't set up at a 20% level, but at a higher level to avoid any issues. The next slide is an extremely dirty shredding and recycling plant. It was looking for a smoke detector solution. From the first visit, it was obvious that no unfiltered, quote-unquote, unfiltered smoke detection could ever operate successfully here. The unique logging and visualization capabilities of open area imaging were used to chart, quote-unquote, chart the environment. Given the extended periods of very high obscuration, somewhere around 60 to 100% while the work was going on, it became clear that no smoke detector could ever be used in this environment. Even if one would accept, actually, traditional type detectors, beams or spots, if you'd accept to ignore the detection during the day when the people were present, the analysis indicated that lens cleaning would have to be done at least on a weekly basis. This is where industrial type air sampling with filters might have been a better fit. Open area allowed us the opportunity to determine that case. Lastly, this slide represents a common challenge in glass ceiling atria, which is sunlight. It's common knowledge that beam detectors shouldn't be set up, including open area smoke imaging, in an east-west direction facing directly into the sun. Traditional beams are known to go into fault in alarm conditions when exposed directly to it. The big difference with dual wavelength is that a fault condition may occur, not an alarm condition, if the imager is blacked out or the signal is lost or attenuated. The UV and IR filters at the imager lens, as well as other techniques, make open area smoke imaging detection very robust at not responding to not only sunlight but other foreign lights and reflections. In this particular scenario, the installer was pressured by the owner due to location of the devices to arrange them directly into the sun. The flat lines in the graph indicate the short period where the imager was saturated due to direct sunlight but only gave a fault condition. That's a huge difference between dual wavelength and traditional beams. Again, dual wavelength can be used in any environment. We've shown you the really hard ones today. And Claudio, I'm going to send it back to you.
Well, Steve, thank you very much. You did a great job presenting that technology. Now we're going to shift gears a little bit into a discussion of applying very early warning smoke detection into industrial environments. We're going to review a couple of basic ASD design approaches and how they impact performance, discuss deployment of ASDs in industrial environments, and then we'll follow it by a few proven field installations. And then, as I mentioned earlier, before we go to Q&A, I'm going to present an ASD requirements matrix that you may find useful in helping select ASDs to meet your specific product requirements. So there are several different design methodologies. Today I'm going to talk about two of them. The first is absolute detection. The second is adaptive detection, followed by a discussion of how these approaches are going to impact performance. So let's move on to the next slide here. And let's talk about absolute detection. It's based on the ability to create a detection platform that can maintain its sensitivity over the life of the detector. One way of achieving this is to utilize a means of keeping the optics clean. This figure shows a clean airstream being passed across the two optical surfaces of the detector. The clean air prevents any smoke or other substances from contaminating the optical surfaces that would ultimately lead to detector drift. This design approach enables you to maintain fixed, consistent, and predictable alarm thresholds throughout the entire life of the detector. But because all environments and background levels are not created equal, the ability to be able to adjust alarm thresholds based on background levels that are present in your environment are important. Here's an example of how it's actually done in the field. The first step is to establish what your background levels are. This is done by measuring and recording the background levels over a period of time. In this case, the average background level is about 0.05% obscuration per foot, with a peak value of approximately 0.12% obscuration per foot. Once you understand the background levels, you're now able to select your alarm thresholds. These are shown by the four green lines on the graph. The four alarm levels selected for this site were 0.25, 0.37, 0.7, and 0.62% obscuration per foot. Adaptive detection utilizes mathematical algorithms to compensate for detector drift caused by non-smoke particles entering the smoke chamber or electrical interference induced into the detection system. There are two components, short-term and long-term drift. The short-term drift is compensated for by utilizing smoothing algorithms to eliminate short-term non-smoke interference sources. Long-term drift is addressed by adjusting the detector's sensitivity to compensate for changes in sensitivity due to non-reversible contamination or component drift. This method of detection relies on the ability to predict the rate at which both smoke and contamination enter the detector, or the ability to differentiate between smoke and contamination. The ability of these detectors to compensate for varying environmental conditions result in self-adjusting, drift-compensated alarm thresholds that can change throughout the life of the detector. The next few slides are going to show basically how these design approaches can impact performance. In this particular example, a smoke test is performed on an adaptive detector. The white line on the right-hand side of the graph is the detector's output during the smoke test. The red line, horizontal red line, are the alert levels of the detector. You'll see that during the test, it actually self-adjusted 3 times, resulting in a significant detection delay. What's important when selecting an adaptive-based detection system is to confirm that the fire and contamination scenarios that you expect to occur in your facilities are compatible with the compensation algorithms used in the detectors that you're considering. Dirt and dust have always been environmental challenges for smoke detectors, regardless of being spot type or aspirated type. But compared to spot detectors, aspirated smoke detection offers more options for dealing with dirty environments. In many instances, all it takes is a good pipe network design to prevent dirt from reaching the detector. We've already discussed how background compensation can be used to compensate for background levels when you're setting your alarm thresholds. When the background levels or dirt levels are too high, inline filtration can be used. And it was with any system, good maintenance practices such as periodic pipe cleaning or installing blowback systems can always help in dirty applications. Over the years, there have been several patents that have been issued that use multiple wavelengths to discriminate between different particle sizes. These techniques are used to discriminate between white, gray, and black smoke, but they can also be used to distinguish between smoke and other particles such as dust. The utilization of particle size discrimination for dust rejection is really an enticing idea, but it raises a fundamental question. Are you rejecting smoke, dust, or both? This conundrum arises due to the fact that large smoke particles and small particle dust can be the same size. Discriminating between small particle dust or large particle smoke can jeopardize a detector's ability to detect low energy, smoldering types of fires. These types of fires characteristically generate large particle smoke. What this graph demonstrates is that is a comparison between an absolute detector and an adaptive detector that also utilizes dust discrimination algorithms. From the graph, you'll see that the adaptive detector is less sensitive than the absolute detector, on average 2 times. Additionally, the adaptive detector did not report any smoke readings below 0.1% obscuration. This next slide is a slide based on results from an independent third-party test agency, a test that was performed conducting both absolute and adaptive detectors. Extreme care was to ensure that both detectors were installed identically. You'll see the pipes are virtually next to each other with sampling holes next to each other. And we also made sure that the alarm thresholds were identical. In the first series of tests, 4 standard hot wire tests were performed as described in British Standard 6266. Each smoke was conducted in different locations within the test area. The result shows that the absolute detector took between 130 and 220 seconds to reach its first alarm level, while the adaptive detector failed to alert within 300 seconds. In the next series of tests, different fuel sources were used: timber, polyurethane foam, heptane, and paper. The test results show that the absolute detector responded sooner to all fires, both initially and throughout the entire evolution of the fire. The data also indicates that smoldering fires present a greater detection challenge than do flaming fires. Now let's talk a little bit about supervision. Supervising electrical integrity, although mandatory by the standards, is not in and of itself sufficient. Chamber detections must be monitored, and in reality is pretty easily achieved because of the technologies that are used. Light scattering or particle counting are 2 fundamental technologies, and since both of these technologies are active, they lend themselves very well to being monitored. Flow monitoring is also required for all ASD systems, but it's important to note that any flow monitoring cannot be shut off or bypassed without raising the system fault. And then now we talk about filters, and there are several methods that are being deployed when it comes to filter monitoring. Some detectors actually don't even supervise the filter and rely on a flow fault to indicate filter being plugged. And in some cases actually allow you to replace a new or reused filter without even operator confirmation. Other manufacturers use a timer to track filter life. An active means of monitoring filter life is achieved by the use of particle counting techniques. And recently, a new intelligent filter has been developed that actually quantitatively monitors the actual filter's performance. This is an example of time-based filter monitoring. Fundamentally, what it points out is that because time-based monitoring does not take into account the environment that the detectors are installed, filter failure or the ability to detect smoke can occur due to high dust loading prior to the filter's time limit being achieved. In this particular example, the detector filter is reported as satisfactory by the system, even though the detector's sensitivity was dramatically reduced by over 60%. Previously, I mentioned a new filter technology. Here's what makes up that filter. It basically consists of a dual sample paths, dual flow sensors, and a HEPA filter. The air enters the filter from the top, from the sampling pipe. And at that time, it's split into two airstreams, one larger than the other. The smaller airstream is left unfiltered, while the larger airstream is passed through a HEPA filter that removes contamination. Then both of these streams are recombined, creating a sample that actually has reduced contamination levels. The recombined stream is then enters into the detection chamber. The ratio of the two flows is measured throughout the life of the detector and is used to optimize sensitivity over the detector's life. So now let's move on to a discussion of deploying ASDs in industrial environments. So if I were to survey the audience today and would ask about ASDs, a general perception in the market is that the ASDs are designed for use in clean environments, and that applying them in industrial environments is just beyond their capabilities. This perception, it remains true today, even though ASDs have been successfully installed in industrial applications for more than 10 or 15 years. This skepticism is due in great part due to the fact that special system application engineering was required before an ASD system could be installed to an industrial environment. And it basically is a result of product shortcomings in the ASD products themselves that led to the need for special application engineering or extensive maintenance to keep them operating properly. So to eliminate the need for special application engineering and extensive maintenance, basically there are a few product shortcomings that have to be overcome. These include the need for secondary protective enclosures, the ability to have a longer pipe runs required because many industrial facilities are just larger and require longer pipe runs. Better visibility of the status LEDs would be helpful because we know that industrial spaces definitely have less than optimum lighting present. But perhaps the most problematic of all features, again, gets back to filtration. The use of external filters requires high level of servicing and maintenance. Eliminating the need for external filters would overcome many of the obstacles in applying aspirated smoke detectors in industrial environments. Additionally, a product with field serviceable modular components would not only reduce downtime, but also reduce spare part inventory and inventory cost. And as we see aspirated smoke detectors entering into more industrial environments, a need exists to establish a minimum performance level as it relates to contamination resistance for aspirated smoke detectors. A new aspirated smoke detector has recently been introduced in the market, and it has a set of unique features that include an IP54 enclosure. It's equivalent to a NEMA 3R, intelligent filtration, 1,200 feet pipe capacity, high-intensity LEDs, and 100% serviceable modular components. The image to the left shows how ASDs have historically been deployed in industrial environments. You'll note that the ASD is installed in a secondary protective enclosure to protect the unit from the ambient environment. You'll also note that inline filters are installed in a pipe inlet to remove contaminants. The image on the right depicts how the same unit, designed specifically for use in harsh environments, would be deployed. There's no secondary protective enclosure or the need for external filters. These enhancements in and of themselves can lead up to a 60% reduction in total cost of ownership. In addition in addition to eliminating the need for secondary enclosures and external inline filters, you could further reduce the total cost of ownership by going to the completely modular design. This eliminates the need to have complete emergency backup units on hand, and would significantly reduce the number of spare parts required. In this picture, basically seeing all the major components of this system are easily replaced in the field by trained personnel. Modularity is also going to reduce the amount of downtime when an inadvertent failure occurs, because you're only going to have to replace the impacted component and not have to replace the entire detector. We're going to change gears a bit now and have a quick review of 4 applications that have been installed with this product. 2 installations are in the U.S. and 2 installations are in international sites. A major power company in southern United States selected and installed this detector to protect their boiler feed pumps. Boiler feed pump fires are a common occurrence in power plants. The pumps are used to deliver high-pressure lubrication oil to the turbine's bearings. It's common that the bearings over time and other joints leak lube oil, and it releases the lube oil into the insulation surrounding the equipment. Over time, the lube oil accumulates and ultimately builds up to a concentration where it can ignite. Conventional spot smoke detectors just can't survive the ambient temperatures of this application. A boiler feed pump fire can result in shutting down both the boiler and the turbine, costing the utility millions of dollars. What's interesting that literally within a few days of installing this particular detector, a small fire was detected. So small that they were able to walk up to it and extinguish a fire with a small handheld fire extinguisher. They replaced the installation, and the production power generation continued unimpeded. This same company also decided to standardize on the same detector to protect their battery rooms against both fire and gas leaks. To cover the gas, what they did is they added a multi-oil aspirated hydrogen gas detector to their aspirated smoke detection system. This next is an interesting example. It's a major U.S. steel company, and what they had is a need to protect the tunnel that was located under a 300-foot electric-fired reheat furnace. The furnace utilizes nitrogen to create a protective atmosphere within the furnace. Their primary concern wasn't fire. It was actually about protecting personnel that regularly walked through the tunnel on a 24-hour basis. They were concerned that nitrogen leaking from the furnace or nitrogen leaking from the delivery system would create an oxygen-deprived environment in the tunnel. The company's original intent was only to install fixed-point gas detectors, no smoke detectors. They ultimately decided to install a combination ASD plus gas detection solution throughout the tunnel to protect, one, against oxygen deprivation due to the potential nitrogen leakage, but 2, to fire that could come from cabling that was co-located in the tunnel. They had totally overlooked the possibility of a fire in the space until they walked through and realized that they did have a source of fire with their cable. So they were basically able to kill 2 birds with 1 stone. This is an example of one of our initial sites that was used to verify the detector's suitability in industrial environments. Basically, it was installed side by side in an existing unit protecting conveyor belt areas in a sugar mill. The unit circled in red is a prior generation unit, and it's housed inside a secondary enclosure to protect the unit from the environment. Whereas the new picture, or the new detector, was basically able to be installed without a protective enclosure. This particular detector has been installed since April of 2011 and continues to operate. The Colliery, interesting. It's a coal mine located in Australia, and it was another trial site. This site was selected because we basically couldn't think of a much harsher environment to truly test and challenge the product. One aspirating smoke detector and 2 carbon monoxide detectors were installed within the mine. 4 pipes were used, range in length from 130 feet to 230 feet. The system monitored conveyor belts, drive shaft units, and pit isolator areas throughout the mine. This is actually some pictures from within the mine. Pretty nasty environment. These units are performing well and providing invaluable information regarding the performance of ASDs in harsh industrial environments. This particular detector is now has been installed since March of 2011 and remains operational today. I like this slide. It's a nice graphic, and basically it shows the evolution of aspirated smoke detection technology over time. If you start on the left-hand side, it basically shows you that initially we targeted ultra-clean applications, semiconductor clean rooms, data centers that basically had little or no contamination issues. The next phase of ASD took us into various manufacturing and warehousing applications where contamination was more prevalent. This is where the use of inline filters actually evolved. And as the harshness of the environment increased, so did the need for project-specific application engineering as well as enhanced maintenance routines. With the introduction of an industrial aspirated smoke detector, the routine use of ASDs are going to increase into this space, while the need for application engineering support and the enhanced maintenance regimes will be significantly reduced, if not eliminated. But, it's not a cure-all for everything. Having everything that I've said, there are still some very harsh environments where application engineering and enhanced maintenance is still going to be required. Now, before we start our Q&A session, I'm going to propose an ASD requirements matrix for your consideration. The idea is to lay out a simple matrix that you can use to perform side-by-side comparisons between various available technologies. And here's an example of how you might do it. When you're looking at technology, just ask yourself some questions. How important is it to have consistent alarm thresholds? Do you need to have deterministic alarm thresholds that you could dial into a particular value, or relative thresholds acceptable? Would you like to be able to compensate for environmental background levels that are basically going to be different in different locations, even within a facility? And how important is flow monitoring that can't be bypassed or tampered with? And is active filter life monitoring really required, or is a simpler method as time-based monitoring sufficient? The last bullet point, the ability to quantify contamination resistance, this is targeted right at harsh environments. Currently in our industry, there are no benchmark tests to assess a detector sensitivity resistance to contamination. So this proposal is intended to establish that baseline. So the test basically, consists of using an ASHRAE 52.2 dust type. It's a silica-based sand. We'd load detectors at a dust loading density of 16 milligrams per cubic meter. We'd have a dust cycle that would be a 3-hour dust duration, 3.5-hour dust duration, followed by 30 minutes of clean air, followed by a smoldering cotton test. Do that a couple of times, and then repeat that cycle 10 times. And then we basically believe that any detector suitable for use in harsh environments should definitely not have a sensitivity drift greater than 15%. Now, this test in and of itself is not going to guarantee 100% satisfactory performance in harsh environments, but it will establish a benchmark for the marketplace for ASDs intended to be used in harsh environmental environments. It's also a test that's going to be able to be confirmed by any independent third-party test agency. I've had a good time presenting today. I hope you folks have learned a lot. I'd like to thank you. And now I'm going to turn it over to Morgan for some Q&A.
Thanks, Claudio. Excellent job. So several folks have already submitted questions, so we're going to go ahead and jump right into answering those. While our presenters are answering your questions, please take a moment to answer the feedback form that will appear on your screen. If you have pop-up blocker technology enabled, we ask that you disable it so that you can receive the form. Okay, first question. There's been several questions that our attendees have asked related to kind of maintenance issues in dirty environments. And specifically, one question was, what enclosures are available to prolong the need to clean the lens of the OS ID system in a consistently dusty environment?
Well, thanks for this question. There's two sides to answering that. That basically means if dust will be dropped down or will attach to a unit, whether it's in a box or whether it's standing on its own, it really will not make a hell of a difference. Now, we've seen people providing a compressed air little pipe that in dusty environment will keep the lens clean continuously, or will do a puff whenever is required. Now, the second thing, of course, is that the dust on the lenses is continuously monitored, and whenever we reach the level of like 20% contamination, we will signal that lenses needs to be cleaned. Now, because we signal that, it does not mean that at that point in time detection is dead. It will still continue to detect alarms. It just means that to provide a good range of detection, the lenses should be cleaned so that they don't obscure totally, because on a total obscuration we cannot detect anymore. Next, please. Okay,
thanks, John. Say another question that's been asked by many of our attendees has to do with the listings and certifications by independent laboratories like UL Canada, FM Global. So what listings and certifications does this system carry?
Yes, thanks, Morgan. This is Wayne. I'll take that question. All the products that we presented here today are UL and ULC listed for the North American markets, and many of them, most all of them, except for the very most recent ones, are FM approved also, and those the most recent ones are in the midst of that already. So if you have FM type work going on in the short period of time, those newer products will have that also.
Okay, thanks for that. Say, one of our attendees has asked regarding the examples that were cited. For example, the chicken farm. Was the fire detection required by code or standard, or was it just installed because the owner had some unique loss prevention goals?
The typical example is from Europe, and there's no code that these farms must have detection, but the user was very interested in protecting his assets, and we were very keen on running a site there as well, because with regard to animal farms, there's not just the chickens. We also run some tests on cow sheds and stuff like that with similar events. In a number of cases, there's a real very high value. If you think in the same take about race horses and similar, there's huge value there, and that requires a decent protection.
Okay, thank you. A good question from one of our attendees has to do with buildings under construction. As you may be aware, particularly with very large buildings, it's not unusual to occupy portions of the building while other parts of the building are still under construction. So they're asking about the suitability of technology like this for buildings that are under construction.
I would say that if that building under construction, of course, has a closed roof that we're not exposed to the elements, that OSID would be an excellent choice, because it really can be deployed extremely rapidly. For those who were attending other proceedings, or the first one on the technology itself, you would remember that the emitters can be battery-powered, offering a 5 years lifetime, and which means that basically only the receiver would require to be connected on 24 volts, and that receiver could be connected to a local fire alarm control panel, or even in certain cases directly to a mobile connection or anything along that. So it would really be a very, very rapid deployment that can be changed and swapped around to new buildings and eventually or progressed and be replaced by a permanent detection afterwards. It would be an excellent application for these sort of buildings.
Okay, thanks. Another question has to do with the use of these systems in environments that are usually very dusty. Will the ambient dust that is present in these environments affect the ability of the system to detect a fire during the dusty conditions?
Are we speaking OSD, or are we speaking aspirated smoke detection, or both?
I'll probably answer it for both.
Okay, I'll shoot off with OSD then. Obviously, one has to quantify what a continuous dusty environment is. If you would have environments that exceed 60-70% obscuration on a permanent base, obviously I would not recommend the use of OSD there, and that's where the ASDs that have been showed would be a much better fit. But whenever the permanent dust is reasonable and within like a 20% permanent deployment, there would be absolutely no risk of missing any alarm, and the whole secret lies that there is a differentiation between UV and IR, as both of these frequencies or wavelengths are emitted permanently. We will see a differentiation for real smoke between UV and IR, and as soon as we see at least 10% differentiation for a consistent period of time, which is, I'm talking seconds, not minutes, the algorithm will detect that there is really smoke. And if that UV signal would reach the set alarm level, we will definitely detect a smoke alarm, irrespective of the background or the dust background.
Okay, thanks. The question regarding an early part of the presentation, you showed a matrix that compared the various technologies available, and the question had to do with what was the basis for the values that were put into that matrix.
I'll take that one, Wayne, since I created it. You know, basically, when you look at our organization, we probably have thousands of years of application expertise when it comes to special hazards. And as I mentioned in the presentation, it's a qualitative list, it's a pretty comprehensive matrix. I'd be happy to contact whoever had that specific question and be happy to explore it in greater details. But it's a qualitative, semi-quantitative assessment of literally hundreds of years of experience in special hazards for that type of application. Again, it's a large open area with high value contents. I could come up with a scenario that would change a matrix completely if, again, that's how it was created.
Okay, thanks. I think this is going to be the last question. We had a few folks ask this about the use of this system in humid environments.
Sure, I'll take that one, Morgan. Either way, whether it's the beam detector or the ASD, they both can survive in that type of environment. They're listed up to 93% humidity, so it's obviously they're already listed for that, so they'll survive. But in extreme humidity, where condensation is known to be an issue, we know at ASD, with a pipe network, as you could imagine, you have a long pipe networks, which actually will help drop that condensation out of the sampled air. And what we've done in many, many cases where there's big temperature differences between the sampled environment, the air that's coming back to the detector, and the detector itself. So we can use a piping configuration called a water trap, and we can capture the water before it makes its way to the detector and causing problem with the detector. And we've done that very successfully in many applications. So that can be done quite easily during the installation period for minimal costs. It's just piping and a couple of fittings. So it's nothing too financially onerous.
Okay, thanks. Well, I'm afraid that we have run out of time. So on behalf of the Society of Fire Protection Engineers, I'd like to thank everyone for joining our webinar today. And special thank you to Xtralis for sponsoring the event for us this afternoon. And I wish everybody a productive remainder of the day.